Example 189. The following data shows the score is given to two different products, A and B, by 10 different judges. Use the Wilcoxon signed ranks test to determine if product A has a higher given median score by the judges. Okay, so this is a dependent scenario, and the reason why it's dependent is because essentially you have the same judge ranking each product. And the reason why they're doing this is because they know, some judges may be harsher than others naturally, which means that they may give overall the products a lower ranking. And if you didn't separate it up in this way, if you didn't use this sort of block design here that you're using, then what would happen is maybe that if, say product A was accidentally assigned to the most harsh judges, and product B, if it was assigned to other judges that were more lenient, product A may suffer by the fact that they have a more conservative set of judges. And so by doing it this way, you make sure that the differences between the judges' tendencies in voting doesn't affect the overall product performance. Because, even if Judge 1, for example, is harsher than Judge 4, Judge 1 would still vote one product higher than another. So if you're only comparing across the two, it makes more sense, and you can still conclude that, Judge 1 felt that product A was better than B, for example. Okay, so anyways, that explains why they used the design they did. It's a dependent scenario, so we're using the Wilcoxon sign ranked procedure. Let's start with the claim. So the claim for the problem, according to this one, which is stated here, is that use the Wilcoxon rank test to determine if product A has a higher given median than the other one, right? So if product A has a higher given median score. So that means that the median for A is greater than the median for B, right? If it has a higher score than the other one being B, then would say that the median for A is greater than the median for B. All right, let's do HOHA then in that case. So the claim here, having the greater than symbol, becomes HA. So we're going to use that here. And then for HO, of course, you're going to express the opposite idea, which is less than or equal to. All right, and now once we have that all taken care of, now we're going to look at the data step. The data step would normally involve us doing the subtractions. Once we do the subtractions, we take the absolute values. Once we take the absolute value, we find the ranks of those absolute values, but they've done all that for us. So all we're going to really do is to come up with those two important quantities, T negative and T positive. So this is going to be the rank totals for the two different categories. So when you look over here and look at the negative numbers, what are the sum of the ranks for those negative values? So if you go across here, we see that the rank is 2. So let's put 2 here, plus, there's a negative 2 here that was ranked 5, so plus 5. And then we have another negative number that had a rank of 2 as well. So we have those ranks for the negative values. Now, the other values are going to be all the positive ones, which we'll add together in a moment. This one adds up to 9, of course. Let's do the rest then. And by the way, you can get this from subtraction. The reason why we'll be able to get it from subtraction is we don't have any ties, right? So we have 10 unique pairs. So our total rank total, if you remember what we said before, would be 10 times 11 divided by 2. So 10 times 11 divided by 2, that'll give you 55. So in other words, our rank total should be 55 minus 9, so T plus should be 46. Let's confirm that, though, by adding up all the numbers that were associated with positive values. So if we take this number, we'll have 5 plus 7.5 plus 2, right, plus 7.5. Oops, I made a mistake there. Sorry, when I was typing that in, something happened. So let's try that again. It'll be 5 plus 7.5 plus 2 plus 7.5 plus 9 plus 5 plus 10. And sure enough, when we add them all up, we get 46, which is what we expected to get. All right, so this becomes 46. Remember that it's the smaller of the two that becomes our test stat. Our test stat is equal to the minimum of T negative and T positive. So we really didn't even need to get this 46. I just did it as a check, really, because once I saw that this one was 9, I knew it would be the smaller of the two, and it had to become our test stat. All right, now once you have that, you're going to do our critical value step. To do the critical value, remember what you want to do. You want to accumulate certain information from the problem. You want to know, for example, what alpha is. So when I look at our problem, does it give us an alpha in the problem? Well, I don't see one, right? It just says use the Wilcoxon sign rank test to determine if the product for product A has a higher given median score. So I'm just going to go ahead and assume that it's 0.05 because it's not given as anything else. Then from there, I want to come up with the idea of whether it's two-tailed, one-tail, right? So I look at HA and I see that it's a right-tailed test, or in other words, one tail. So I'm just going to write one tail here. And then lastly, I want to get the N, the sample size. So how many total ranks or values do we have, or pairs of values? Well, we had 10 values here because we didn't throw out anything because of ties. There were no ties. So we're going to go ahead and say that N is equal to 10. Okay, so with N equals to 10, with alpha being 0.05, and looking at a one-tailed test, let's go figure out what our critical value is. Remember, we'll call that critical value T0. Okay, so let's go to the table and figure out what that is. Okay, so we're at the signed rank test table, and we're looking for alpha of 0.05 in one tail with N being 10. So again, we're looking at alpha 0.05 in one tail and N being 10. That's going to give us the value 11, right? So we're looking for the value in the first row because we're in the 0.05 one-tailed where N is 10, and we get T0, our critical value, to be 11. Okay, so T0 turns out to be 11. All right, now that we have that value, we're going to compare it against our test stat. And remember the rule, if T is less than T0, we're going to reject HO. Otherwise, we do not reject HO. And in this scenario, I think that's true, right? We can see that T is only 9, while T0 is 11. So since it's less than, we're basically able to reject. And it's actually less than or equal to. Sorry if I just put less than. It's less than or equal to. So since 9 is less than or equal to 11, we're going to conclude that we should reject HO. And remember, if we're rejecting HO, we support HA. So we're going to conclude in this problem that we're rejecting HO and we're supporting HA. And with that in mind, then looking back at the claim, we'll say, hey, we support the claim. So in this problem, we were able to support the claim. Incidentally, I've been mentioning that when the non-parametric procedure is used, it's generally a weaker procedure than using, say, for example, here, the dependent t-test. But if you're able to reject the null hypothesis the way we were, we don't have to worry about that because it was able to reject the null. When it's weaker, it means that it has a harder time rejecting false null hypotheses. If you reject the null, then you don't have to worry about that issue because it means the test seems to have been powerful enough to detect a false null hypothesis. We were able to reject it, so we don't have to worry about this conclusion, at least with regard to the power of the test. That's not something to be concerned about here. So we were able to reject it. We support the HA. That means we support the claim, basically. And so we are saying that product A seems to have a higher ranking from the judges than product B.